Okay, I want to take a poll here. Who has taken 61C? Can you raise your hand if you have? Okay. Who remembers anything of 61C? Okay, I saw the ratio drop by half. Okay, does the word cache sound familiar to anyone? Okay, great. So, we're going to be talking a lot more about that. Now, in the prereqs, we do list 61C as a prerequisite for the course. That said, if you haven't taken it, you can still do well, and I know a lot of people that have. It'll just require paying a little bit of extra close attention to this next unit, because it is probably the first time that you're seeing things like LRU or MRU. So it's, that might be a little bit tricky at first. So if you haven't taken 61C, I strongly recommend paying very close attention in this lecture. Because this is one of those things where it might move a little bit faster if you haven't seen it. Stop me if at any point I'm not making any sense. So, what have we done so far? We've managed to talk about the SQL client. You guys did your project 1. And then we jumped all the way down to disk space management, and we did files and index management as well. We talked about B+ trees, we talked about slotted pages, fixed length pages, etc. But we didn't really talk about the part in the middle. We didn't talk about the buffer manager yet. So far all we've said is, we're searching for a page, and then we go to disk and we pull it, and then we work on that page. Okay, but I haven't actually addressed how you do that, or what specifically pulling a page from disk entails. So, let's go through that. Today we're going to be talking about the buffer management layer. Once you're done with this, we'll have completed the bottom half of a DBMS. So you can think about it as like the middle layer between the files and index management layer and the disk space management. And it basically, its role is to provide like a RAM-based API for that higher layer, so that it can pull pages from disk and you can work in RAM. And what that means is basically in RAM, you have a whole bunch of pages, right, or a whole bunch of frames. And in those frames, you can pull in and copy pages from disk, and you'll basically provide access to the layers above you to these pages by pulling them into memory, and then there's an API that other layers higher up will use to then interface with memory in that sense. So maybe this will be a little bit clearer. Basically, let's say the files and index management layer will issue a request to read a page or write a page. What it's actually doing, let's say we want to fetch page 1. So you're going to tell the buffer manager, hey, give me page 1. Files and index management, that layer wants to work in memory. And if the page isn't in memory, this layer, the buffer manager, is basically responsible for pulling the page into memory so that the layer above can continue working as normal, right? That layer above, the files and index management layer, those layers above want to depend on the fact that when they're working on a page, that they're given the illusion that they can modify these pages and access them in memory. And this layer is going to be responsible for constructing that illusion. Are folks on the same page with me so far? Okay, give me a thumbs up if you are. Okay. So let's say I get a request to read page 1. Now what's going to happen here? Page 1 is obviously not in RAM, so what am I going to do? The buffer manager is going to say, oh wait, well page 1 is not here yet, so I'm going to send an API request to disk. I'm going to copy page 1 into memory, and the layer above can now access page 1. What if I get the request to read page 2? Same thing. Send an API request to disk, move it up into RAM. Buffer manager has now done what it needs to do. The page is in memory, and now the layers above can work with it as needed because they will interface with the buffer manager to access those pages. Now, here's the nice thing. Now, if files and index management layer once again wants to read page 2, well, it's already in memory. So there's no need for an extra read from disk, which, as we knew from the previous lectures, a read from disk is very, very costly. Remember the analogy I used? RAM is like going to Sacramento, and disk is like going to Pluto. Here, we stored the page in RAM. The buffer managers basically stored it in RAM, and now, when I read page 2 again, I have avoided that extra trip down to disk because it's already stored and cached in RAM. Okay? And so now if I send a request for page 3 isn't there, so I'll load it into memory again. And that's basically how this overall interface goes. If the page requested is not there in memory, buffer manager will interface with disk manager to pull that page in, copy it in rather, and paste it into one of these empty frames. And then the layer above can, operate as needed. Okay? So that's the high level overview. But there's a couple things we haven't actually gone through in detail. Like, firstly, what happens when someone actually writes to a page in memory? I mean, we're not only going to be doing reads. At some point, we have to write as well. And when we write, well, how do we ensure that the writes we do are actually persisted to disk? Because what happens when we actually pull a page into memory? We're copying that page from disk into memory. But when we modify that page in memory, now what's on memory is not the same as what's on disk. We've updated it. At some point, we have to make sure that page, which is now dirty in memory, it's modified, that update has to persist. So what happens? How does the buffer manager know when a page is dirty? How do we keep track of that? How do we handle dirty pages in general? And secondly, what happens when, you'll notice here I had a finite amount of frames. So what happens when I actually run out of frames and I still need to pull in pages? What do I do? How do I kick out pages from memory so I can load more into these frames? It's like bullets in a gun, right? You only have so many chambers. So you need a way to decide how you can replace pages as needed. So let's start with the dirty page aspect first. Does the term dirty page sound familiar to anyone from 61C? Okay. Largely yeses from the audience, so let's continue. So let's assume that that we modify a page. So we're going to have this picture to kind of denote that the page is modified in memory, that it's dirty now. Okay, you have the squiggle on it at the pencil. Okay? So how is the buffer manager actually going to find out that that page is dirty? You don't actually, in real life, when you're actually implementing it, you can't just draw a squiggle on a page. It's all nice for visualization, but doesn't really work when it comes to the actual ins and outs of it. So how do you keep track of when a page is modified? And the answer is we're going to store something called a dirty bit. There's going to be a dirty bit on the page, and that's going to indicate by its value, 1 or 0, whether the page is dirty or whether it is, not, whether it just hasn't been modified. Now the other question is, what would we do with a dirty page? And the answer is we're going to write it back to disk via the disk space manager. Right, so the buffer manager will interface with the disk space manager, write it back. Yes? How often do we need to write back dirty pages? So that's an implementation question. How often do we need to write back dirty pages? That is more of an implementation question, and it depends. Firstly, are you kicking out a dirty page from memory? If you are, you need to write it back. How frequently will that happen? That really depends on the task that you're doing and the different tasks that are running in your system. So it's really more of a system / application / program dependent question. Now there are some more advanced questions here as well, which is what happens when there are concurrent operations on a page? Or what happens when there's a system crash? We'll tackle those questions later in the course. I want you guys to know we're not forgetting about them, but for now, to simplify the understandings and assumptions, we're just going to proceed without really handling these things for now. We'll touch on these in about a month or two. Okay? So, this will be the visualization for what we use for a buffer manager state. Okay? Now, if you want to see what that looks like in memory, well, what it really is, it's a large chunk of memory that's just malloced by the DBMS at startup time. Okay? And it's dealt with in, there's a large chunk of memory, typically in the megabytes or gigabytes, that is malloced by the DBMS at startup, and it's dealt with in these frames, which are like page-sized chunks of memory. Remember that, okay, at one point I do want to clear up something with everyone. Does everyone know what an I/O is? Okay, give me a thumbs up if you know what an I/O is. There are decidedly less thumbs up than I would like. Okay, would someone like to give their explanation of what an I/O is? Anyone? Okay, yeah? Yeah, basically. An I/O is a read or write to disk. A unit of transfer from memory to disk. You can think of that as an I/O. If I modify a page in RAM, that's not an I/O. You can modify a page in RAM 100 times, that's not an I/O. But when I write it back to disk, that's one I/O. When I read a page from disk into memory, that's one I/O. That unit of transfer, disk to memory, that's an I/O. Okay? So, back to the buffer manager state. It's going to basically malloc this large chunk of memory, and it's broken up into, you can think of it as being broken up into page-sized chunks. And what does that table actually store? There's this table written here that will kind of indicate what we're tracking in the buffer manager. This is a table of metadata. And what that table of metadata stores is the frame ID, which is where in memory which frame you're dealing with in the buffer manager. The other thing that stores is the page ID, which is which page is in the frame. So in frame 1, what page am I storing? Okay? It also stores whether the page is dirty or not, the dirty bit. Okay? And then, what else? We're going to have something called a pin count. Okay, this pin count, we're going to get to in a second, but that basically tells you if the page is in use and how many tasks are operating on that page. Okay, and this is what you might see in metadata. And this is a sample illustration, what it might look like, with actual values populated. Of course, instead of the N and Y in dirty, you can imagine a 0 or 1. But that's just like a smallish array in memory that's also malloced at the start time, and that'll help you keep track of what's in your buffer manager, including the dirty bit, et cetera, et cetera. Okay? Okay. Illustration here. This is how you would kind of draw out to visualize what the buffer manager would look like. You've got these 6 frames. They're not necessarily in order, you notice that it's not page 4 corresponds to frame 4, et cetera. There's not a perfect mapping like that. Okay? It's the pages which are in the frames. They would be drawn accordingly. So frame 1, page 1, frame 4, page 6, frame 5, page 4, and you can see that via the table here. Okay? We've squiggled on the page to indicate when it's dirty, such as page 2. We have pins on the pages that are in use. So you can see page 2 has a pin count of 1, which indicates that one program, one process, is accessing page 2. Page 6, which is in frame 4, has a pin count of 2, which again indicates 2 programs / processes / tasks. They're accessing page 2 at that given point. Okay, so now here's a nice boxed illustration of it. Yes? Yeah. Oh no, we'll go over that. When does it know when to write to disk? We'll go over that later on in the lecture. Right? For now, don't worry about that for now. We'll go over that pretty soon. But for now, just think of it as metadata table. This is what the visualization's like. I just want to set the stage for what we're going to talk about in a little bit. But is this part clear to everyone? Okay. All right, so here's a nice boxy illustration that people might like to see. But anyways, let's talk about a little bit of terminology. So the page pin count, as I said, number of tasks using the page, okay? And if the buffer manager is full, what page should be replaced? This is something else that we have to decide, okay? And the answer to that is we need to refer to the page replacement policy that we're going to use. Some of you may remember from 61C terms like MRU, most recently used, or LRU, least recently used. What those terms refer to is how you decide to kick a page out of memory. Okay? So, one thing to ask, if a page is pinned, can I kick it out of memory? Okay, I see a bunch of people shaking their heads no. Why not? Exactly, yeah. You would ruin whatever's using it. Yes?
What happens if all the stuff in memory has like pieces in it?
All of the stuff, yeah, then that's a problem. And at that point, you get into trouble. You know, things could hang or whatever. And so a good DBMS, a well-implemented DBMS, will actually have it so that it avoids that case as much as possible. Of course, if you overload a process, that's kind of your own fault, but like, ideally, the point is, by keeping pins on for as little time as possible, we minimize the number of pins on the pages at any given point. Ergo, we don't end up in that scenario where every page is pinned. But yeah, if every page is pinned, you are kind of exactly where I was when I entered an exam without studying at all, in a bit of trouble. You might also do what I did, which is cry, but you know. Yes?
So about the number of tasks, is that like the number of queries running in parallel, like currently running, or what is the task?
So what is the task in a DBMS? So for example, if you're writing to a page, right, if there's a program that's writing to a page, that could be considered a task. So, you know, if I'm doing an update operation and a transaction comes along and it's writing to a page, that's a task. If the term transaction doesn't sound familiar, just think of it like a process, a program. Like, say you're doing like an update operation, you know? Like update into for a table. That. Okay, so when a page is requested, there's some steps we need to follow. If the page is not in the pool, if the requested page is not in the pool, we're going to choose an unpinned frame for replacement. We know it's unpinned if the pin count is equal to 0. If the frame is dirty, now someone asked, when do you write a dirty page back to disk? This is one of those cases. If the frame is dirty, you're going to write that page back to disk and mark it as clean. Okay? Then you're going to read the requested page, the page that you wanted, into that frame. Okay, so at this point you've kicked out the page occupying that space, that frame, if there was one. And now you have a frame that you can read your requested page into. Okay, once you do that, you're going to pin the page and return its address. You're going to pin the page and you're going to give it back, give that returned address back to the requester, which will then do what it needs to do with that page in memory. Okay, so you might ask, why do we need to pin that page? Well, we want to remember that the requester is working with that page right now, okay? Because once we load it into memory, that's not enough. We can't just stop and say that's not. No, it was loaded into memory because someone asked for it, right? A trip to Pluto, a trip to disk is extremely costly. You're not going to undertake that out of the goodness of your heart. So if you're pulling a page into memory, it's probably there for a reason. You don't want to accidentally screw it up either by saying, oh, hey, well, yeah, now that it's here, whatever, I just did it even though no one wanted it. No, someone asked for it. The requester is going to be working with that page right now. Or if it's not working with that page right now, it probably will be very soon. So we're going to pin the page once it gets loaded into memory. Okay, is that clear? So when a page is requested, choose an unpinned frame for replacement. If that frame has a dirty page on it, write that dirty page back to disk. Load the page you requested into that frame, then pin the page, return the address. All right, now one optimization you can do is if the request can be predicted, like if you know you're doing sequential scans of a page, you can actually prefetch some more pages. For example, if I've requested page 2 and I know I'm doing a sequential scan, well, maybe I want to prefetch pages 3 and 4 as well. That's an optimization. Why? Because remember in last lecture I said sequential reads are like 100 times faster than random reads? Does anyone remember that stat? This is a classic example of one that's useful. Right? While you're there in disk, you might as well load as many pages as you can. So if you know that you're going to be doing a sequential read, you might as well pull in a couple more pages while you're at it. Okay, so let's walk through an example of page replacement here. Let's say that you want to read page 7. And let's say that, right now, everything is full. Okay, so if we wanted to, for example, if we wanted to kick out page 2, let's say that's what our replacement policy dictated. Let's kick out page 2. So you're going to have an API request to disk. You're going to need to read in page 7, write back page 2. And you'll then pin page 7. And you'll return a pointer for its address. Okay? So after the requester finishes working with that page, the requester of the page must set the dirty bit if the page is modified. Okay? It needs to also unpin the page, and preferably soon. Otherwise, if requesters hang on to pins longer than needed, you end up in that scenario where you have pretty much all the pages pinned and it kind of sucks because you can't do anything because you're bottlenecked. Okay? A page in the pool might be requested many times, so that's why we have something called a pin count, and you're going to increment the pin count to pin a page. Okay? So, a page is a candidate for replacement if and only if its pin count is 0. Right? Now, like I mentioned earlier in the lecture, there's other modules like concurrency control and recovery. They might actually do some more IOs, but we're going to ignore that process for now. Just think about what I've said in steps 1 and 2. Yes?
Why is it that the page can be simply unpinned like immediately after it's been like abandoned? Like why the preferably soon, and why isn't it just like immediately after?
Sorry, I'm not sure I understand the question.
Well, the parentheses explains that like the requester has ended that task, and it can take time for it to be like unpinned. But why doesn't it have to just immediately after?
Oh. Okay, yeah, no, basically what it's saying is that the task, hopefully that task itself requires the page for very little time. So you optimize the implementation of the task so that it doesn't actually have to access that page in memory for very long. Like a write, it would just be like, okay, once I write this page, that's it. I can, stop working with that page. Someone else can use it now, like that. Does that answer your question? And that gets into the heart of something we'll be talking about later in the class with transactions, about locking and unlocking and releasing locks. But I wanted to avoid going into too much detail with that here because we might confuse a couple people too. Okay, so let's try to answer some of the previous questions that we had said, which was, number one, how is the buffer manager going to find out if the page is dirty? Well, there's the dirty bit for the page, right? There's a dirty bit on the page. That's how you can kind of tell. What do you do with the dirty page? You're going to write it back to disk via the disk space manager if you're going to evict the page at some point, right? So when the page is evicted, you can't just say, oh, cool, well, it's dirty, well, bye-bye. No, no, no. If it's dirty, we have to write it back to disk so that they stay synchronized. We don't lose information. We also asked that question about page replacement. How do we know if a page is in use? How do we ensure we aren't just kicking out a page when someone's using it? There's this process of a pin count. And the last question, which we haven't really answered, is if the buffer manager is full, what do we do? What page should be replaced? So let's get into that. Okay. Okay, so the page is chosen for replacement by a replacement policy that we're going to decide. There's some terms here that we're going to throw out for now. LRU, which is least recently used. There's most recently used, and then there's a clock replacement policy. Okay? Now, some of you may have heard some of these, some of you may have not. That's okay. We'll go through each of them. Okay? But what I want to stress is that the exact policy you choose can have a very big impact on the number of IOs. And it's important to choose the right policy for the types of tasks that you will be doing. Now, how do we know what's the right policy to choose? It really just depends specifically on the task that you're doing, the access pattern of the pages. When you know the access pattern, you can pick the right policy to choose accordingly. But let's talk first about the least recently used policy. Okay? Can someone give me, just a rough explanation of what they think LRU does? Yes. Least recently used, it's right there in the name, you're correct. Basically, we're going to kick out the page. If the buffer manager is full, if all the frames are taken, we're going to kick out the frame that has a page that was least recently used. So you can see these timestamps here. 43, 21, 22, 11, 24, 15. You're going to replace the frame which was least recently accessed, least recently used. Okay? That's what LRU is all about. It's as simple as the name makes it sound. Okay? So really, truly don't overthink it. It is exactly what the name makes it sound. But there's a couple of things here that we might want to be cognizant of. Number one, what is it good for? So it's pretty good for when you have repeated access to popular pages. So for example, when I load a page into memory, if it's very frequently accessed, its timestamp will also be very recent. Ergo, if I keep using it over and over, I probably won't kick it out of memory, so it will stay there for easy use, easy retrieval. So basically what it's good for is not kicking out pages that we very frequently use. And that's important. There are a lot of cases in which this is really, really critical. But this can kind of be costly. So why can it be costly? I mean, it seems pretty good for IOs, right? You don't, the pages that you need seem to stay in memory more than they don't, so what's up? Well, the answer is, let's walk through an example here. How do I tell which page is the one to replace? How do I tell which page was least recently used? I would have to scan through this table, which is a linear time search. Okay, so you can say, well, we could optimize it. Who says you need to scan through the table? Let's have like a mini heap. I mean, we could have like a priority heap of sorts. That's 61B went over that. Does that word sound familiar to anyone, priority heap? Great, so we can use that. But that's still log n time. And log n is good, but not good enough. We want to get as close to constant time as possible in practice. And so maybe something that we can do is we can try to approximate LRU through an algorithm that will give us, constant time access / constant time replacement determination. And so people developed this thing called the clock algorithm. Okay? So what does a clock algorithm actually do? So it's exactly like what the name makes it sound if you want to visualize how it works. We're going to literally draw a clock. That might sound weird, but it actually works, and it works really, really well. The clock hand is going to point to the next page to consider. The next frame to consider, so to say. And there's going to be an addition here in the clock. There's going to be this concept of reference bits, which have recently referenced pages. What does that actually mean? Well, remember in LRU we had timestamps. Right? We had timestamps indicating when pages were accessed. But that we can't actually store anymore, because remember what the problem with those was? The problem with those was to maintain the minimum timestamp, we would have to use something like a priority heap, which would take log n time. So instead what we're going to do is something kind of similar, but we're going to simplify it a little bit. We're going to say, okay, let's make a trade-off here. Let's just track whether a page was recently referenced or not by a bit, a 1 or a 0. That bit will just tell us, was this page recently used? And based on whether a page is pinned or unpinned, and then whether the bit is set or not, if the hand points to it, we can decide, is that frame a candidate for replacement? Let's take a look. Before I go into the illustration, this is kind of what an explicit table for the clock policy might look like. You've got, instead of the timestamp that you might have seen here, the last used timestamp, you're going to have a reference bit. And then you'll have a clock hand indicating the frame that you're on. Now, let's walk through an example to figure out how the clock policy actually works. Okay? Let's say a request comes in. Say, read page 7. Okay, first let's check. Is page 7 in here? No. Okay, so page 7 isn't in there, so we need to load it in. How do we decide what to kick out to load in? So the hand will point to the first frame that we want to consider replacing. We're going to check, can we replace this? All right, can we replace this frame? What's it pointing to? It's pointing to the frame with page 2. Can we replace it? No. Why not? Okay, guys, a little bit. Thank you. Okay, it's pinned. So, we're going to skip it. Let's move on. Let's go to this one, page 3, frame 3. Can we replace this? Well, it's not pinned, which is good, but there's a reference bit. That reference bit says, hey, I was just in use. You can't replace me yet. Okay, so we say, all right, fine, let's move on. But I came around and you weren't in use this time, so I'm going to clear your reference bit. I gave you a chance to prove that you were in use. You weren't here. Next time I come around, if you're still not in use and you haven't been used, you're out. It's that second chance. So we're going to clear the reference bit. We're going to advance the clock hand. Now we get to frame 4. Can we replace this? Yes. So we're going to replace it. We're going to bring in page 7. We're going to pin it. We're going to set the reference bit, right, because it's in use. And then we're going to advance the clock hand. And we're going to return a pointer to that page. Okay? Okay. Here is the pseudocode. And I think while folks copy this down, because I think this is something people might want to copy, I personally don't actually find it very useful. I find the illustration and working through it much better for myself. But you know, I find that some people actually do enjoy looking at the code and learning through that. And so, if you want, take a second or two to copy this. I'll come around meanwhile, see if anyone has any questions. Okay? 8:15 right now. Let's give it about 3 minutes. Okay? All right, so let's get started again. Let's now think about what we just learned. It's a very intuitive, very simple policy, LRU and clock. LRU, we know the benefits of. Clock is an approximation of LRU. It's not exactly LRU, but in practice, it's a good enough approximation of which pages have not been recently used to where you'll get good performance with it and you don't have to maintain your min heap data structure. Okay? But there's sometimes these things work really well, like repeated access to popular pages, but there's also times at which this starts to fail. Like if you're going to repeatedly sequentially scan a file, like you might do in joins, and we'll cover that in a little bit. If you're going to repeatedly sequentially scan a file, this type of thing sucks. So let's walk through a couple of examples soon about this. Okay, let's do a repeated scan here. We're going to repeatedly scan through the file on disk, okay? Page 1, page 2, page 3, page 4, page 5, page 6, okay. So far, everything we've had has been unavoidable. No one can possibly be blamed for having cache misses. I mean, you've never read that page before. So far, it's whatever. Now, let's see what happens. Page 7 comes along. What was the least recently used frame? Okay, 1. All right, I still haven't had a cache hit. Now I go back to page 1. All right, surprise Pikachu FaceTime. Now, guys, I'm only 25. I'm going to use memes, okay? Like, did anyone see we had like Pog on the first lecture slide? Okay, anyways. Oh, come on, half my TAs play League of Legends and Valorant all the time. Like, I'm kind of used to the terminologies by now. Anyways, now we go back to page 1. Well, sucks. So we're going to bring in page 1 in the spot where least recently used was page 2. Great. Now I'm going to read in page 2. Uh-oh. Okay. So does everyone see how we keep missing stuff? Let's play that again. We just kicked out page 2. Least recently used page now. So now we need to load in page 2 again, and it'll go in the slot of page 3, correct? Okay. So we've just had a case where we replaced page 1 with page 7, then we needed to access page 1 again. So we said, okay, fine, let's replace page 2 with page 1. Okay, all fine. Now we need to read page 2. We're like, oh, great. Replace page 3 with page 2. Okay, that's what we just did. Now we're going to read page 3. Great. We're going to replace page 4 with page 3. Now we read page 4. All right. Does everyone get the picture here? Okay. This is called sequential flooding. This is exactly why LRU is not always the best case. Okay. Give me a thumbs up if you understand why LRU might break sometimes. Okay. So we managed to do something incredible. We had a 0% hit rate in the cache. I mean, if I had literally just kept all of the frames static but 1 and just kept kicking out that 1 frame, I would have done better. Well, that's an idea. Okay, let's think. Hang on a second. What could be better? Repeated sequential scans often happen. They don't always happen. When they don't, LRU is pretty good. But they do exist, and to pretend that they don't, that's not good. How do we handle the case when they don't? What can be better? let's bring in a policy called MRU, okay? First things first, we're gonna have to have 6 cache misses. Okay, we'll have 6 pages in the cache. That's all right, unavoidable as usual. Okay, now, most recently used does exactly what the name says it does. We're going to replace the most recently used page. And you might think, why would I do that? In the case of sequential scans, this is very good. What is the most recently used page here? 6. Good. Okay? So we're going to kick out page 6. 7 goes in. All right, we still have no cache hits. Now we're going to start scanning again. 1. Oh, hey, 1's in there. Great. 2. Oh, cool, 2's in there too. 3. Wow, nice. 4. 5. And now 6 comes along. And now we're like, well, we did kick out 6, which is a bit awkward, but hey, the other guy did that too. The other policy did too. And what's better, we got, 5 cache hits out of it. All right, so great. We're done patting ourselves on the back. Now we actually need to do something about this. Okay, so we're going to load in page 6 into memory. Where are we going to load in page 6? Can everyone raise your hands and just tell me where? Okay, 5. 5 is the most recently used frame, so 6 is going to go there. Now we're going to go to 7. Oh, hey, cool, 7's in there. So, it's great. Now let's try again. 1 is there, 2 is there, 3 is there, 4 is there. 5 is not. Okay, now let's replace page 4, because that's the most recently used. Okay, so you can see how MRU is actually very good for sequential scans. This is the limit of what it generally ends up approaching. Okay, this is the general case for it. In limits, it typically approaches a B-1 divided by N-1 hit rate. There are N pages in the file, B pages in memory. Am I good to move on? Do you guys want a minute more? Okay, 1 minute more. While I'm waiting for people to write it down, if you understood what clock was, no need to bother listening to this joke of an analogy, but I kind of think it's funny. So, does anyone here remember studying in main stacks or in Moffitt or whatever? I guess back when that was a thing before the pandemic? Okay, good. At least some people nodded, so I don't feel that old. Okay, so, y'all remember when you'd walk through and it's full during dead week? And you'll see you'll see an empty chair and it has papers and notebooks and binders on it. And you're like, oh shoot, someone's probably here, right? Then you come back 2 hours later after not having found a seat. So you go somewhere else and you come back 2 hours later. And the same notebook and binders are still there and no one is there still. So you're like, you know what, screw it. And you just move their stuff and you sit down and you'll deal with the consequences later. Has that ever happened to anyone? That's kind of like clock. It's that second chance. Technically, I don't know if you're supposed to do that, so don't tell anyone I said that, but whatever. Okay, we're moving on. Okay, so here's an improvement for sequential scans. You can prefetch data. So if you know you're doing a sequential scan, you can ask your disk space manager for a run of sequential pages. So on page 1, if you have a request, you'll be like, hey, while you're at it, can you get me pages 2 to 5 as well? It's kind of like when you ask your little sister to go downstairs and get you like a granola bar or a glass of water, and it's like, hey, while you're down there, can you get me an apple also, and an orange, and a banana? And then eventually she comes back and throws the things at you, you know? Okay, but why does this help? So it basically amortizes your random I/O overhead, right? Sequential reads, way better than random reads. Okay? And it allows computation while these I/Os continue in the background. Okay, so basically, if you're asking which one we need to implement in practice, the answer is that we kind of need a hybrid. LRU wins for random accesses, right? Hot pages versus cold pages. You might see something like that in web pages, for example. Most frequently used web pages, like that. But MRU wins for repeated sequential scans. You're going to see that happen with joins. Okay, so let's sum up what we've learned today. The buffer manager basically provides like a level of indirection, mapping page disk IDs to RAM addresses. Okay, memory has like, there's a chunk of memory mallocked, and then you can think of it in like page size chunks, like frames. You're going to load in pages from disk into those frames. And the buffer manager is going to ensure that each requested page is pinned in RAM. Then it'll be manipulated in memory, hopefully briefly, and then the caller, the requester, will unpin it. And the key here is you just need to minimize cache misses. Okay, and how do you do that? You're going to replace pages that are unlikely to be referenced anytime soon at least, and you're going to prefetch pages that are likely to be referenced soon. These are optimizations you can do. Okay. What do you want to make sure you know from here? Make sure you know pin counts and dirty bits. So when do they get set? When do they get unset? When do you pin, unpin a page? And what unpins and pins a page? Okay? LRU, MRU, and clock. We want to make sure that you can run these things by hand. For clock, walk through the illustration. Do a few problems by hand. Walk through the illustration. I promise you, once you do 3 or 4 of them, you'll be very good at it, and then you can just kind of cache that away in your mind for exam use. Okay? Make sure you remember for clock what pages are eligible for replacement, what the reference bit is, when it's set and unset, and what that reference bit is actually for. If you get bored, think of my analogy for main stacks. I didn't say to do it, I just said to think of it. Okay? Also make sure you guys know about sequential flooding and how it behaves for LRU and MRU. Okay? So, a couple of things to go over briefly in terms of, I guess, overall course logistics. We finished quite early today in terms of content. It's only 7:34. I'll stick around in case people have questions, but before you guys go, I'm going to go over a couple of things. Okay? I think a couple Mondays from now is President's Day, so we're not going to have lecture then, obviously. What I want to hammer through, though, is make sure you guys get your Project 2 started early. Okay? Reason I say this is because this is always going to be one of those things where people do Project 1 and they say, oh, it's pretty easy. I'll start Project 2 2 days before it's due also. Then you end up in slip days because there's an annoying Java bug you can't figure out, like we all run into, and yeah, that's when problems begin. So let's try to make sure that doesn't happen. Start early. Second thing I want to go through now is academic dishonesty. Okay? All right. Please stick around for this part. I do want to make sure everyone gets this. Okay, so every semester this happens, where people end up getting, you know, stressed out or whatever, and they make a bad decision, and for some reason or another, you know, things happen, and they ask their friend, can I take a look at your code? Because I've been debugging forever, and then before you know it, you kind of, I guess I've seen students just copy it over. Okay. There's a lot of safety valves built in this class to help you avoid this, okay? We have slip days. There's 5 of those. Please use them. They're not there to bank on bonus points at the end of the semester. They're there in case life happens, okay? Sometimes slip days might not be enough. Sometimes there's a scenario where life comes up. Okay. I realize the reputation Berkeley has, but I was also a student 2 years ago, so I know what it's like. We have an extensions form up for this very reason. Okay, if something comes up, if you're extremely sick, for example, or you had an unavoidable family emergency, come and talk to us. I promise you, we're not robots. We understand things happen. We will accommodate if something that bad happens. Okay, I had students last year where, or in the past even, where, you know, huge family emergency comes up, or their health emergency comes up and they cheat because they don't have enough time. Don't do that. Just tell me, okay? We'll work through something else. Promise it'll be okay. But once you cheat, then we can't do anything. Then, as per university law, and as per course policy, then we actually have to pursue the case and send it to student conduct. I don't want to do that. So instead of doing that, I'm asking you guys now, please start the project early. If you can't, if things happen, and you feel pressured, don't cheat, it's okay. Come talk to us. We'll work something out, okay? We need to enforce guidelines and fairness, but I don't like enforcing these things, so please just make sure that y'all remember the rules. I mean, you guys are mainly upperclassmen now, you know the drill. So let's try to avoid unpleasant situations, because I really like teaching this class, and the only one part I don't like is when Dylan is like, hey, so there are these mouse matches, what do you want to do about them? And I'm like, oh, great, really? So yeah, okay? Anyways, thank you for coming, everyone. That's all I have for lecture today. I'll see you guys on Monday.